In today's video, we're going to talk about capacitors. We'll talk about the different types of capacitors that you'll run across, some of their basic characteristics, and the applications where you'll use each of these different types of capacitors. Certainly the most common two types of capacitors that you'll run across and use are multi-layer or monolithic ceramic capacitors and electrolytic capacitors. So let's talk about both of those first. Let's start with the electrolytics. Probably the most common electrolytic capacitors you'll run across are the aluminum electrolytic. And I've got some radial and axial-leaded examples here, as well as some surface mount parts. The electrolytics are typically, from about 1 microfarad to maybe well over 1 farad, with some working voltages from 5 volts to sometimes well over 500 volts. Just about all of them are polarized. There are some non-polarized examples that you can get, non-polarized electrolytics. They're typically used in like audio crossovers for speaker crossover networks, but the vast majority of the electrolytics you'll find are polarized capacitors. And they'll be marked as such. They'll usually have one side or the other, usually the negative side, marked on the aluminum electrolytics. They're typically used for things like power supply filtering for relatively low frequency applications, typically below 100 kilohertz. Because above that, their self-resonant frequency starts getting in the way, and they don't really work like very good capacitors anymore. They do have an unfortunate wear-out mechanism, especially accelerated by heat, that causes the electrolyte within these capacitors to dry out, which causes the ESR, or dissipation factor, to rise. That causes an increase in temperature with ripple currents, and that accelerates the failure. And that's a very common failure mode for these types of devices. They also have some what we call soakage or dielectric absorption issues. And what that means is that if they've got a DC bias applied to them for a while, and then you short the capacitor out to discharge the capacitor, then remove the short, some voltage will actually come back due to the polarization that happened within the electrolyte. I'll actually show you this here in a moment. It's pretty interesting. The other thing about these electrolytic caps is that the leakage increases pretty dramatically with temperature. The capacitance will also change with temperature. So, and if you've got an application where you need to do rapid charge or discharge, like for flashes and things like that, you generally need to specify special parts, because your ordinary aluminum electrolytics aren't designed for high currents like that. But they do have a very high capacitance density per unit volume, and that's what makes them very popular, because they're really good for things like power supply filtering. You'll often see them next to power supply regulators, and other places where you want to quiet down a bias or something, bias voltage or something like that, because they're really good for low frequency power supply decoupling and bypassing. They're also pretty good for low to medium frequency bypassing, in amplifiers and things like that, but aren't used. There's certainly applications for them there. They can be used for some non-critical low frequency timing applications, but because of things like the absorption characteristics, the temperature changes, and especially the some of the instabilities, you don't want to use them for anything where you need any critical kind of timing. But energy storage applications, great. Low frequency stage coupling, between one stage or another, they're just fine. You typically do not want to use them for critical timing circuits, as I mentioned. Triggering circuits, where you need a really precise amount of charge stored there that you might use to trigger another circuit. And definitely not in any circuits where you need precise frequency determination or phase shift circuits. And they generally don't have any place in any RF circuits because of the relatively low self-resonant frequency. Just because it's so interesting, let's take a quick look at this soakage or dielectric absorption issue. So here's just a little 1 microfarad electrolytic capacitor that I've charged up to just about 12 volts. You can see on the voltmeter there, it's just about exactly 12 volts. Now if I pull the power supply off of this, you can see the voltage is starting to drop. It's just leakage and some current that's going into the meter. But let's short these leads out here. So I short the leads out, we can see we've dropped down now to, there's 200 microvolts. But watch what happens when I remove the short. That voltage is ramping back up again, and pretty soon here we are at 75 millivolts, 80 millivolts. It's going to go well over 100 millivolts here. So we're ramping up here, and now we're at 125 millivolts, and now we're at 1% of the voltage that I was applied to it before. And I had that discharge from an electronic standpoint a pretty long time. Let's short that out again. get back down here, down around 3 microvolts there, 3 millivolts. Let go of it again, and we see it ramping up again. And this is, again, dielectric soakage, and it can really wreak havoc with precision timing circuits. So before we leave the topic of polarized capacitors, let's talk about the other type that you'll see, and that's typically these tantalum capacitors. And I've got a couple of examples here, some radial-leaded and then a little surface mount device here. Tantalum caps are all, again, they're all polarized, and I would say they're wildly polarized, and I'll tell you what I mean by that here in a moment. But they're typically, ranging from, about, 0.1 to 1 microfarad up to 1,000 microfarads or so, but they're relatively low voltage. They won't go up to the hundreds of volts typically that the electrolytics will. They do have a higher capacitance density than the electrolytics, so for a given package size you can get a larger value of capacitance with the tantalums than you can with the electrolytics. They are very intolerant of reverse bias. So, a little bit of reverse bias on an electrolytic, it may leak a little bit, you might accelerate the failure mechanism, but they're going to be pretty tolerant of it. The tantalums can get pretty exciting. When tantalums fail, they generally fail short circuit, and then oftentimes will burn, catch fire, cause some damage and things like that. So as long as you treat them right, they're actually pretty good, reliable capacitors, but do not overvoltage them and do not reverse bias them. And they don't have the wear-out mechanism that the aluminum electrolytics do, but they are pricier than the aluminum electrolytics. They generally have got nice low ESR. They're a bit more temperature and voltage stable than the aluminum electrolytics are. But again, they're a little bit pricier, so you do have to pay for that. So the applications are very similar to the aluminum electrolytics. Good power supply filtering, low to medium frequency bypassing, energy storage, and long duration timing. Again, that is not super critical, although the soakage characteristics and tolerance characteristics of the tantalums are generally a little bit better than the aluminum electrolytics. But they're not good for high voltage applications or cost sensitive applications, of course, or anything that's got any large AC signals that might even momentarily reverse bias them. And similarly, their self-resonant frequency is low enough that you're not going to really use them too much for RF applications, although the ESR of them is a little bit better than it is with the aluminum electrolytics. Now, outside of the low-frequency power supply filtering and decoupling caps and things like that, you'll most likely find ceramic capacitors. They're certainly the most common that are out there. And with most modern electronics being surface mount, the vast majority of small surface mount capacitors are these multi-layer ceramic devices like are shown here. Lots of different package styles, from the disc capacitors to these kind of molded monolithic type devices and dipped monolithic devices like that one there. Now, the capacitance and voltage range for these can range anywhere from under a picofarad to well over 500 microfarad, and even available with working voltages to well over 1,000 volts. Now, there are a lot of different types of ceramic capacitors, and they're kind of divided among the different types of dielectric and the characteristics of that dielectric. The Class 1 dielectrics, different types called NP0 and C0G, these Class 1 devices are very, very stable devices with temperature. They may only vary by a few percent over a very wide temperature range. They're available with a very tight tolerance, but they're typically low-value devices, from less than a picofarad to maybe up as high as a microfarad, but typically, tens of nanofarads or less. Now, because they're low values of capacitance and they're very stable, they find themselves to work very, very well in RF applications, and that's where you'll find these are very common there. Now, the Class 2 dielectric materials, they vary a bit more with both temperature and with applied voltage. So they're not quite as precise, they're not quite as stable, but they are available in larger values. Now, the letter designations actually will relate to the temperature range and the amount of variation that they have over a given temperature range. It's probably worth a whole other video just to talk about that, but we'll just kind of leave it at, put some of the common values that you'll see here. Some of the common Class 2 dielectric types that you'll see are X7R capacitors, Y5V, and Z5U. These are all kind of Class 2 dielectrics. If you take a look at this little chart over here, This is a chart showing the relative capacitance change versus temperature. And this very shallow little linear line here, that's your MP0 and C0G capacitors. The X7R capacitors might vary plus or minus 10 or 15% around their original value or their nominal value over that temperature range. So that's not too bad, but that's still a pretty good variation. The Y5V and Z5U, they're kind of horrible when it comes to temperature variation. They may go up as high as 10 or 15% over their nominal value, but drop down to 60 or 70 or even 80% of their below their nominal value at the temperature extremes. They also have got a higher dissipation factor, and both of the class 2s are somewhat voltage dependent as well, where the capacitance will change with applied voltage. But you get larger capacitance values. So you'll find that the Y5V and Z5U caps, they're available in very large values. They'll be used for non-critical bypass applications where you can accept that kind of a large tolerance in the value. The X7R is a reasonable compromise between the stability of the class 1 dielectrics, but the larger values of the Y5V and Z5U materials. So if you have a choice for a given value in your application between X7R caps and the Y or Z type caps, go with the X7Rs. They're going to be a bit more stable. All of the ceramic caps are generally pretty low cost. They've got low dissipation factor, low ESR, good RF performance. But the ceramic materials are also microphonic. So if they're in a high vibration environment or things like that, that can actually cause the capacitor to become a little bit microphonic, almost like a quartz type of device. So you have to kind of be aware of that. So again, typically good for RF applications. They're very low cost, bypassing interstage coupling, decoupling around gain stages and things like that. They're good applications for that. Generally not so good for use in voltage-controlled oscillator designs or frequency generation designs because of the variation over temperature. The class 1 like MP0 and C0G are the exception here. They certainly can work very well in those applications. And they're not really good for low frequency filtering where you can't really withstand this kind of tolerance with temperature. So especially the Y5V and Z5U are really bad. An X7R wouldn't be so bad for that application, but very, very common types of capacitors that you'll find all over the place in many, many different package styles. Now, something I'll mention at this point is if you're reviewing a schematic or you see something online you're going to go build and the capacitors aren't labeled in terms of what types they are, whether they're ceramics or electrolytics or film or mica or whatever, the most likely case is that any of the polarized caps are electrolytic caps, and in many cases could be substituted with tantalums. Any of the others that are non-polarized, generally lower value caps, they're most likely ceramic capacitors. If the application really warranted something other than those two, hopefully the schematic would be labeled that way. But it's a pretty safe assumption that for the polarized caps they'll be electrolytics, non-polarized or ceramic. But that being said, let's go take a look at some of the other common types of capacitors that are out there and some of their characteristics and see where they'd be applicable. Probably the next most common type of capacitors are the film capacitors. Now they're, again, just like the ceramics, there are many different types of film capacitors. One of the differences though here is that there aren't that many film capacitors that are available in surface mount, or certainly not nearly as many as there are for ceramic. But there's actually some really nice characteristics of film capacitors that make them worth taking a look at. So some of the things that film capacitors have in common is that they're generally available from the low tens of picofarads to in the neighborhood of even 1,000 microfarad, very large values, and working voltages from relatively low voltages to well over 1,000 volts. So very wide capacitance and voltage range. Generally, the film caps have got really tight tolerances and very low leakage, very low absorption, very low ESR and dissipation factor. All really good characteristics for capacitors. They're very stable with temperature and voltage, but they're moderately to high priced with respect to ceramics. They're relatively large. They don't have as good of a volumetric efficiency, capacitance per unit volume, that the aluminum electrolytic or the tantalums do, but they're also not polarized, and they're going to have a probably not even as good of volumetric efficiency as even the multi-layer ceramic caps. They are available in two kind of broad different types. There's a metallized film or metal foil and film. So we talk about film capacitors because what we're talking about is the dielectric material, the insulator between the two plates of the capacitor is some type of a film, plastic type of a film typically. And that film can either be metallized on one side and then rolled up, and that's the metallized film capacitors. They've got the highest density because you don't have a separate foil in there. Where the metal and foil film is, you've got alternating layers of plastic insulator, metal foil, plastic insulator, metal foil, and that's rolled up. They generally will have a lower ESR, they can operate with higher AC currents, but they're not going to have as high a value because they're not as, you don't get as much capacitance per unit density with those. But that's kind of the common characteristics of these film caps. Now, as I mentioned, there are many different film types that can be used in these film capacitors, and they have some slightly different characteristics that make them useful for certain applications. The polyester or mylar caps are very, very common, and they're moderately stable with temperature, 5 to 15% variation over temperature. They're pretty good with dissipation factor, a little bit higher than some of the other types, but they're generally lower cost. Probably the other most common type is the polypropylene or PP type caps. Polypropylenes are very common, like these orange drop caps or the brown drops over here. They're generally very low absorption, they're very stable with temperature. They're just a bit pricier than the polyester or mylar caps. One of the problems though with some of these types of caps, like a polypropylene and polyester, is that you can't often tell from the packaging what type it is. You can get a mylar cap or a polypropylene cap that looks like it's packaged the same way in these little plastic encapsulated packages here, rolled up in these type of axial type of devices or dipped in some of these others. I've seen the polypropylene and polyester in both of those package styles, so you can't always tell by looking at them what they are. You can be pretty sure that that it's a film cap, but you can't necessarily tell what type of film they are. Now, some of the other types of film is a polystyrene capacitor. These are really stable with temperature with very low dissipation factor and absorption. A little bit harder to find. They're pricey. I don't have any here. Oftentimes, what these look like, they look almost like a clear tube, like a clear plastic tube, almost like a glass diode, if you will, but it's made of plastic with like a foil inside of it. They're not really good in operating in very high temperature environments, like next to a vacuum tube or next to some power resistors, because the polystyrene plastic itself will begin to deform and melt. But but in applications where it's low power type applications, are actually are pretty superior to some of the other films. But they are harder to find, they're a little bit pricey. Polycarbonate caps, very high reliability, they're also pretty pricey. Performance is about the same as the polypropylene. There are lots of other different types of film caps that different types of films that are used, and you almost have to look up and see what the characteristics are. But the two most common that you'll come across will be the polypropylene or the polyester, with the polypropylene generally being the higher performance of the two. They're really good for high voltage applications. They're really good and stable with temperature and voltage. They got pretty low dissipation factor and dielectric absorption, and they're really good from everything from audio to RF applications. The downsides is that they're pricey, they're physically a bit large, and they're a bit limited in the package styles that you can get. These film caps are often the ones that, if you're doing some restoration of old antique radios and things like that, you're going to be replacing some of these early film caps. These are old paper and wax, so it wasn't really a film that was the dielectric, it was actually a paper that was used. So it was like paper and foil wrapped up and then stuck in the tube and sealed with wax. These capacitors by now are all kind of dried out and leaky and all need to be replaced. And replacing them with mylar or polypropylene caps is the most common thing that you would do in these type applications. Now, one other point I'll make about these film caps, especially those that are wound up like a coil here, is oftentimes you'll see they've got a band marking on them. that would make you think that they're polarized. Well, the reality is they're not polarized caps. They're not like the tantalums or the aluminum electrolytics. What that band indicates is which terminal on the capacitor is connected to the outer foil wrapping. So if you think about it, you've got basically an insulating layer and a conductive layer that are wrapped up. So one of the conductors is going to be on the inside of that last wrap. The other conductors will be on the outside of that last wrap, with the insulator being in the middle. So the band indicates the outer wrapping is connected to that wire. And oftentimes in the electronics, what you're going to want to do is connect that to the lowest potential, lowest voltage potential in the circuit, so that you don't have a high voltage on the outer perimeter of here. But there may be applications where you may choose one end or the other to be connected up in a certain part of the circuit to prevent coupling to the capacitor. Like you might want to connect the outer foil edge to the lowest impedance node in the circuit. But that's why these film capacitors are often marked with a band. You'll see them like on that, and even on this this dipped variety, you've got the band marked here. That means that this lead here is connected to the outer foil wrapping of the capacitor inside this molded case. So the next type of capacitor we'll talk about are mica capacitors, where the dielectric material is actually a mica material. Some of the older ones were in these what we call domino packages that typically had these colored dots that would indicate what the value was, and others typically in these kind of molded packages. Again, typically relatively low value, a picofarad to maybe 10 nanofarads or so, but can operate at very high voltages. Mica caps are really stable with temperature, really stable with voltage. They're available in very tight tolerances, not these particular devices, but they are available in some very tight tolerances. And they've got really good RF performance. The dissipation factor is very low. They're very, very commonly used in RF applications, in filters, and voltage-controlled oscillators, or other oscillator or frequency generation circuits. Very commonplace to have mica caps because they're very, very stable. The bad thing is that they're smaller values, they're limited in package styles and things like that. Now, you might say these look an awful lot like those molded film caps. Now, the way you can generally tell the mica caps apart is that they're a bit lumpy, if you will. If you take a look at this package, it's kind of bulged at the ends, or it maybe almost a little bit dog bone shaped, if you can think about it that way in terms of the way the package is, compared to the film caps, which are generally a bit more smooth and I would say cylindrical, or just don't have the lumpiness, especially associated at the ends. That's almost the only way you can kind of really tell whether that's a mica capacitor or a film cap, because the molded caps kind of look the same. But generally, if it's kind of a lumpy kind of a package, that would almost tell you that it's a mica capacitor. And also, you can often tell from the application. If it's in an RF circuit, a VCO, or something like that, if a mica cap was available, it likely would have been used in that application. Now, of course, there are lots of varieties of variable capacitors as well. Some of these larger air dielectric kind of bread slicer variable caps, and the smaller what we call polyvaricons, because they are like a polyfilm variable capacitor. Typically, they've got some trimmers as well as kind of main tuning on them. You find these in some of the older transistor radios. You might find some of these in some of the older larger transistor radios, or tabletop or even tube radios and things like that, to make the tuned local oscillators for tuning the radio around. Then you'll also have trimmer capacitors that might be small little ceramic type trimmer caps. I've got a bag full of different types here. Maybe some compression caps. These guys are basically two plates that, when you loosen the screw, the plates separate, and they'll often have a mica insulator between them. These types of caps obviously are all used in RF applications. Here's kind of a slug-tuned variable cap here as well. Lots of different types of variable capacitors that you'll run across. But in general, all of these are typically used for RF applications, where devices like these two are designed to be kind of tuned and operated all the time, whereas the trimmers are typically set and adjusted to tune or align a circuit, and then they're left alone and never adjusted again, so they don't have the durability of some of these continuously variable devices. Of course, really kind of impossible to cover all the different types of capacitors and all the specific application and characteristics in one short video, but I hope this brief introduction to the different types of capacitors, their characteristics, and their basic applications and where you'll find them has been helpful. And again, just remember that the vast majority of the polarized caps that you see will be aluminum electrolytic or possibly tantalum, and the vast majority of the non-polarized capacitors you see in a design are most likely ceramic, whereas you could use film capacitors or even mica capacitors in those applications, particularly if you're operating at over a wide temperature range or at higher frequency. So I hope it's been helpful. If you like what you see, give me a thumbs up. If you haven't subscribed already, please do so. And we'll see you again next time. Thanks for watching.